Obviously, we cannot talk about monsoon variability without going to the subseasonal timescale. The early evidence from cloud band data from satellites was used by Sika and Gadgil to write some nice papers. There were some earlier studies also talking about these timescales in the Indian region by Yasunari, for example. To quote Sika and Gadgil, the presence of two ITCZs, we already mentioned this several times, a continental one in the north on a majority of the days, and sometimes simultaneously an oceanic one in the equatorial belt of the northern hemisphere. Epochs of oceanic ITCZ are characterized by very long lifespans only when continental ITCZ is absent. We'll see the diagram in a minute, the figure. Thus, the atmosphere is faced with the choice of forming an ITCZ in the warm oceanic regions near the equator, or over the heated continents to the north, or a combination of both. It is seen that the choice made consists of a combination of both, with the continental ITCZ being dominant most of the summer. We've seen that in many ways. So here is the same thing showing for different years, 77, so 73, 74, 75, 76, and 77. 72, 73 was actually a fairly strong El Nino, but in this figure it's not easy to see that. In fact, the relation of ENSO with the intraseasonal timescale is also not that clear. But you see this latitudinal band time going this way, the northward propagation, and there are times when there is a anchored cloud band over here called the MCZ, or the maximum cloud zone, and nothing on the equator, whereas it's propagating this way, it's not anchored over there. So it's kind of spotty data, but was used to make some really good points. The northward excursion or the origin in the tropical region also varies. Some, like this one, starts from the equator, goes all the way into the subtropics, whereas this is starting around 10 north, this is hanging around here, and so on. So just like MJOs had the canonical MJOs, the eastward decaying and eastward intensifying intraseasonal oscillations, the MESOs, or the monsoon intraseasonal oscillations, also have inter-event variability, as we will see in a minute. The main thing about MESOs is that the monsoon, if you look on the subcontinent, is made up of these kind of seasonal variabilities. This is showing multiple years, and we'll look at details of these few years. But you can see that there is a interannual variability here with some high frequency variability within each season. And if you zoom in, it becomes fairly obvious looking at 99, 2000, 2001, and 2. This is a El Nino year as well. These were La Nina years. So this is the blue line here is the long-term climatology, which is the same line in each of these plots. And then these are annual subseasonal variabilities in each year. So you can see that there are great differences, and the number of break events which are below the climatology and active events which are above are not the same in each year. For example, here 2001 2, which were droughts, you can see there was one active year in June, and then basically very weak active events, lots of breaks, and then one stronger active event at the almost end of September before the monsoon withdrawal, whereas here there are more active and break events. So there is always this debate about whether droughts are associated with more break events than active events, whether normal years have more active and break events, so that the duration adds up to being normal or above normal rainfall, and so on. And then the question is whether El Nino teleconnections are also associated with the modulation of these active break cycles or intra-seasonal variability within the season. Okay, in general, as I mentioned before, the monsoon literature often focuses on the onset and withdrawal, and then that gives you a length of the rainy season. And there are studies arguing about changes, interdecadal changes in the onset, decadal changes in the withdrawal, which changes the length of the rainy season, and within that you have trends in the rainfall, seasonal rainfall, and extreme events, and so on. So the story gets quite complicated. Nonetheless, if we look at composites of the inter-event variability, taking all the mesos in those few years that we looked at, going from the equator, in fact south of the equator in the ITCZ region, all the way across into the subtropics monsoon trough zone, averaged over the Indian longitudes, you can see that there are generally these so here this is the time day zero, where the convection is centered on the equator. So this is again OLR, of course. So you have the break period propagating to the north, so that the continent would have below the climatological rain. This is the active period, so you can see the propagation speeds and so on. And you have eastward propagating mesos. Out of the 58, 21 have strong eastward propagating mesos, which is clear when you look at the same time period between 0 and 5 north. So you can see a clear longitudinal propagation towards the east. So there is a northeastward propagation, if you will. And in situ mesos, which don't propagate as much, you can see that 0 to 5 north, they are basically stuck at the Indian longitude. This is going off into the maritime continent. And you have the all mesos combined together. So there is a large inter-event variability as well, and we will see some more details when we come to the mechanisms. If you do composites as a spatial structure, we are looking at rainfall, again day zero when it's maximum over the Bay of Bengal and the continent, going 15 days before and 15 days after. Typically you think of pentads, so you're going 3 pentads before and 3 pentads after. And there is the associated surface pressure signature and sea surface temperature signatures. With composites, you always have to be careful, because these are multiple events combined, and the signal gets smoothed out, and you get very coherent looking features, whereas the inter-event differences make it much more noisy. Nonetheless, you can clearly see that there is the break period with convection and rainfall over the equatorial band, and at minus 10 days the break period is waning, and the northward propagation of the rain band is beginning to happen. And by day minus 5 you have clearly the extended wet band here, which has this structure that goes quite large. So you can see that even though we are focused on the South Asian monsoon region, there are signals that go all the way into northwestern Pacific region in the deep tropics across the South China Sea and so on. So it's not a very local feature, and in fact Rui and Wong and others have papers arguing that maybe there are Rossby waves emanating from the Northwest Pacific warm pool region. So at day zero you have strong convection over the Bay of Bengal, almost covering the entire upper bay, and rainfall over the core monsoon zone, which is what is used to define the active period, whereas the peninsular India has the opposite phase with drier rainfall, so below the climatological mean, and the equatorial region has a break period as well. So you have this kind of meridional flip-flop happening here. So rising motion, sinking motion, and rising motion, sinking motion, and then as you go into day 15, you have gone back to day minus 15 in terms of the rainfall feature being on the equator and dry period over the Bay of Bengal and land. Okay, so associated with that, of course, high pressure, low pressure, so the pressure signals are red colors for negative, and then even though there is rainfall here, you have the low pressure is expanding all over, even though you already have subsidence and below average rainfall here, and then the sign switches. So the correlation scale of the pressure is very different than the rain, as you can imagine. SST, again, break period has colder SSTs over here, somewhat of warmer SSTs, and then it flip sign. So you can see that there is rainfall here, a little bit of cold SSTs remaining, but warm, sorry, I should be careful. The negative signs here are positive SST anomalies. So you have clear skies, radiation, warming, so SST getting organized before the active phase, and then once the active phase happens, SSTs cool down. So by the time rain is happening, there is reduced radiation, high wind, mixing, entrainment, and cooling of the SSTs, and then it recovers back to towards cooler SSTs or warmer SSTs as the next break phase comes in. So Vecchi and Harrison, and there are many papers arguing this kind of intraseasonal coupled propagation northward with SSTs leading the convection by 10 to 15 days. But this again occurs when you do composites, but when you look at individual events, things are not always that smooth. Obviously it happens in most events, that's why composites produce that kind of pattern, but there are details and inter-event differences that are sometimes significant. Okay, we'll look at mechanisms in the next podcast, but this sets up the basics of the mesos.